In this video, we're going to introduce where vectors come from, what they are, and why they are useful. So to begin with, let's first consider fundamentally what science is all about. And science, in its nature, is about taking observations of the world and from those observations figuring out how we can quantify them, how we can understand the world around us better through developing a system such that we can predict what events will happen in the future. Now, in order to quantify what we see, we need to come up with a system. And now, a magical fact is that a system of mathematics works fantastically well at describing the world around us. Now, vectors themselves are just a mathematical quantity that is highly useful in describing certain relationships in the world. Now let's take it back a step and just look at an example in antiquity of where these mathematical concepts have come from. For example, say that we have a bag and we have some balls in here, and now you take this bag of balls to your friend and you say, look, if I take half of the balls out and I put them in another bag, and say that we have 4 balls in this bag, then I can guarantee you that I'm going to have 2 in each bag. And now this concept of being able to quantify these balls in the bag as numbers, and then to be able to manipulate them so that by separating them out you can predict how many balls you'll have in the bag, is intuitively obvious for us in the 21st century to understand that this is just kindergarten sense. But yet, back in the day, this was quite phenomenal. And that's why it's taken many, many years for these concepts to become integrated into our society. And now, this particular example here, these entities, these single numbers represented by a ball, or say represented by a sheep in a field, or another example could be, say, temperature, or the number of clothes that you have in your wardrobe. Those are represented by scalars. And now a scalar is just a single number with magnitude that is useful in a lot of situations. But now let's consider another situation. Say that you're here, you're pushing against this rock, and then say that you have a not that nice a friend who's also pushing really hard against this rock in the other direction. And now you're pushing with a force in this direction, and your friend is pushing in this direction. And you want to figure out what is the net force acting on this rock. Well, suddenly, you can't represent the situation with just a single number. Like, to represent the force that I apply as a single number doesn't make sense, because I'm applying a force with magnitude but also with a direction. And this direction here is given by, well, say this angle there. And so, in order to quantify the situation, it's not good enough to just use scalars. We need other quantities. And now this is where vectors come in. And so a vector is a mathematical quantity that has 2 fundamental properties. It has magnitude, and direction. And now, again, why this is so useful is because there's so many situations in the world where we have physical phenomenon that can be modeled using in quantity that has magnitude and direction. And that's fundamentally where vectors get their application from. And now vectors have a specific algebra that's associated with them. Just like numbers, we have algebra. If you add 2 and 2 together, you get 4. And for us, if we take a bag and we have 2 marbles and 2 marbles in another bag, and we put them together, it's obvious that we're going to get 4. Now with vectors, there's the same fundamental principle for addition of vectors called the superposition law, or the parallelogram rule. And all that this says is that if you have one vector in this direction and another vector in this direction here, then the addition of these vectors will be the vector that if you were to draw say that this is A, B, and C, then the vector from A to B added to the vector from B to C will be this vector from A to C. And now this law, it's called the parallelogram law, because if you take this vector A to B, represented, say, as, we'll get into notation later, but say AB, and then this guy here, BC, and now if we add these two guys together, then you can see that AB, if we represent this vector on this side as well, and BC we have down here as well, then you can see that this forms a parallelogram. And the diagonal of this parallelogram, represented by these two vectors that we're adding, is the sum. And now, the fact that vectors exhibit this property is simply a fact that derives from that in the world, whenever we have vectors, we always see this same law being held. Like if you are pushing on a rock with a force in this direction, represented by a vector, and a force in this direction, then the net force is the sum of these forces in such a way that they hold this parallelogram or superposition principle law. And so it's just a fact of nature. And therefore, the quantities of vectors have been derived such that we can model these situations. And that's why these quantities have magnitude and direction, and the superposition principle holds. Because for physical quantities that we can represent using vectors, we get this relationship. Alright, now, where do these come from? Say, if we take another example, like where do we see vectors being used? So if we get rid of this. Alright, we'll say that we have, let's change our color. Say that we have a bank here, and we have some water in this river. So we have a river flowing in this direction with, say, speed v. So this is the flow of the water. And now say that we have on here, we have some form of boat. And so here's our boat, a nice wooden boat. And now say that you're standing on this boat. So here's you kind of sitting in the middle. And then say that you're walking in this direction here. So you're walking towards kind of the western north part of the ship. And now say that you have a friend over here who's on the shore. And he's watching you. And now, how fast is he going to see you move? And now, again, if say that you're moving at velocity of c. So, in this direction here, in 1 second you'll go c units. And now, in 1 second, the boat will flow v units in this direction here. So, what is your friend going to see? Well, the thing is that this situation here can be represented by the fact that the boat, relative to your friend, will be moving v in this direction here, while you will be moving c in this direction here. And so the addition of these vectors is a vector that joins these two. We'll get into vector addition later, but it's a vector that can be represented by the sum of v and c, and this is the velocity that your friend will see you moving relative to his position on the shore. And so the thing is, between different reference frames, vectors can be used to determine the relationship of motion from one frame to another. And this is another use of vectors. And so this is just a simple example. And vectors are all over the place. And we'll get into more of where their properties reside and their applications in later videos.